Welcome to this video on reflections and rotations, the transformations using matrices. Now, any linear transformation can be defined by the effect it has on the unit vectors 1, 0 and 0, 1. This one is 1, 0 and this one is 0, 1. So this is the unit vector 1, 0 and the unit vector 0, 1. Okay, so any linear transformations can be kind of defined by the effect it has on these two unit vectors. So if we have a matrix M, that's A, B, C, D, and those will just be values, it will map 1, 0 onto AC. So this one will map onto this one here. And 0, 1 onto BD. Okay, so map 0, 1 onto this one here. So if I had the matrix C minus 2, 3, 1, minus 1. Okay, so if I'm looking at this one is going to map to minus 2, minus 1. Oh, sorry, minus 2, 1. So in red, this would be, about here. And then I'll do the next one in green. The 0, 1, which is here, would map on to BD, so 3 minus 1. So there. Okay, so that's where they would map, and if I'd have a square, I could look at the third point. So if I had a square, so this one is these two added together, it's at 1, 1. So the new version of that would be these two added together. So it would be at 1, 0. That should be, well, I haven't got a different colour. Which would be here. So, my square in this case would be end up looking something like that, which is, some weird stretch and rotation maybe. But anyway, that's just like the basics, but there's quite a lot to kind of understand and get your head around. Now, there are a couple of things, terminology that you need to know, and these are invariant. So invariant, I think that's spelled right. So invariant points and invariant lines. So an invariant point is a point that does not change. Okay, so in this case, 0, 0 was an invariant point. It stayed the same. And invariant lines are lines that don't change. So if I had a reflection in the y-axis, that would be an invariant line. If I had a reflection in the x-axis, that would be the invariant line. Okay, so that's invariant points and invariant lines. We'll look at that a little bit more when we look at some examples. And speaking of examples, let's look at the first one. So in this example, we're going to look at this matrix, what effect it is going to have on our unit square, which is here. Okay, so this is the the one basically 1001. Okay, so it's just the unit square here, and what effect this transformation will have on it. Well, it'll change the 10, which is this point, into a -10, so over here. And then this one will stay the same. So I'll draw this in purple. It will end up being this purple one here. So a reflection in the y-axis. Okay, so that's what happens with this one. So this point goes from 10 to -10. This point here goes from 0, 1 to 0, 1, stays the same. And then this point, which is these two added together, 1, 1, will go to -1, 1, -1, 1, this point. So this matrix is a reflection in the y-axis. Now let's look at this next matrix here. So this one I'm going to do in red. So 1, 0. So 1, 0. This point here stays the same. Okay, and 0, 0 stays the same every time. And then this point 0, 1 here goes to 0, -1 here. So this is here, and then the final point is 1, -1. So it ends up here where this red one is. So this is a reflection in the x-axis. Okay, so reflection in the y-axis looks like that transformation. Reflection in the x-axis looks like that. Now let's talk about the invariant points, invariant lines. So on this reflection in the y-axis, what are the invariant points, the invariant lines? So invariant line, this x equals 0. So in invariant lines, x equals 0, otherwise known as the y-axis here. And then these two lines, so y equals 1 and y equals 0. Y equals 1 and y equals 0. So those lines are unchanged. Now, in fact, what we can say is, well, y equals k. That can replace these two. Okay, because in fact all these horizontal lines would stay the same. If my diagram went into any of them, they'd all stay the same. But obviously these vertical lines have changed. Like it's gone from 1 to -1. For example, x equals 1 to x equals -1. So those would not have changed. Would have changed, but the horizontal ones wouldn't have. So basically every point on the y-axis would stay the same, and then horizontally would stay the same. And for the reflection in the x-axis, it's, you know, the opposite. So y equals 0 stays the same, and x equals k stays the same. So in this flip, only this is the only horizontal line that stays the same. All the others change. but all the vertical lines stay the same. Okay, so they stay in the same place. Oh, sorry. Right, I kind of made a little bit of a mistake. Just in terms of how I've described these. So I'm going to do a little bit of rubbing out. So the invariant lines are the y equals k. Invariant points are on the line x equals 0. What I've basically done is just a slight error, and let me explain it to you here. So invariant point maps the point onto the same point. So all the points on x equals 0 map onto themselves. And then the lines y equals like k, so y equals 1 maps the whole line onto itself. So it's mapping this whole line onto itself, so the line is staying the same, but not each individual point, because, for example, this point is going here. So effectively, the y values on this line will stay the same, but the x values are changing. So the invariant line is this line, but the invariant points is every point on the y-axis will stay exactly the same, the x and the y coordinate. So I just need to change that on this bottom one. So get rid of that, and then invariant points is on the line y equals 0. So sorry for that miscommunication there. I did think about starting the video again, editing it all out, but I figure now it's nice to see that that everyone makes mistakes. So invariant points are all the points on the line x equals 0 for the reflection on the y-axis and y equals 0 for the reflection in the x-axis. So the points that are on those lines map back onto those points. And then the invariant lines are lines that map onto themselves. So it means that just one coordinate stays the same, the other one changes. Okay, so when we're looking at a reflection in the y-axis, okay, the x coordinates are changing, the y coordinates are staying the same. So that's why there's invariant lines are all the y equals a value. And then when we look at the reflection in the x-axis, so here, all the points that are on the x-axis, so on the y equals 0, will stay exactly the same, the x and y coordinate. But then all the lines, x equals value, they will stay the same because the x coordinate will remain the same, but the y coordinate will change. So that's why they're invariant lines, and the invariant points are the ones where they stayed exactly the same. So hopefully I've cleared that up. There was probably some of you watching this questioning what I was saying earlier. Hopefully now that makes sense. Now let's have a look at the reflections in the line y equals x and y equals negative x. So next we're looking at reflected in the line y equals x. Now these are going to be looking like this, 0, 1, 1, 0. So this will reflect in the line y equals x. So the original here is 1, 0, 0, 1, standard point. And what you can see is 1, 0 goes to 0, 1. So this point goes to this point. and this point, which is here, goes to this point. So here goes to here, here goes to here. So in this case, the diagram will look exactly the same, but like this goes to here and this goes to here. Okay, so for this one, the invariant lines invariant lines invariant points. So which ones? So this is a reflection in the line y equals x. So where are our invariant points? So all the points on the line y equals x will be invariant points. So the points on the line y equals x will be invariant points. Now the invariant lines are this direction. So can you see, like, if I drew a line here through this one and this one, this invariant line would stay the same. It would flip from here to here, but it would map onto itself again. So this is y equals negative x. So it's a negative x in terms of the direction, but then plus k, because it'd be negative x is here, and this would be plus 1, plus 2, and so on. So all these diagonal lines will be invariant lines. Hopefully that makes sense. And then let's look at the other reflection. So 0, minus 1, and 0. So this is a Sorry, I had to pause then. Trying to spell it and say it at the same time just wasn't working. Reflection in the line y equals negative x. So if I'm reflecting in the line y equals negative x, my reflection is going to end up here. Okay, so I can see, you know, this will be 0, 0 will be an invariant point. Okay, and every point on this line y equals negative x will be invariant points. So invariant points will be everything on the line y equals minus x. And then invariant lines will be like this line. They reflect onto themselves, but obviously like this point would reflect down here and this point would reflect up here. So invariant lines would be y equals x plus k then, for like this line and this line and this line and this line and so on. Okay, so these are, you know, all the reflections. Now let's look at, you know, another shape with these reflections. So here we have a triangle, coordinates of which are 2, 2, 5, 2 and 5, 0. Okay, so I'm going to put these coordinates down, 2, 2, 5, 2 and 5, 0. And we're going to reflect it in the line y, in the y-axis. So minus 1, 0, 0, 1. So this time we're going to multiply through. So minus 2 minus 5 minus 5, and we've got 0 plus 2, 0 plus 2, 0 plus 0. Okay, so that is my new shape. So minus 2, 2 here, minus 5, 2, minus 5, 0, there, and there. So there is my image of A. So a reflection in the line, in the y-axis, the line x equals 0 there. Okay, let's do a reflection in the x-axis. So 1, 0, 0, minus 1 times by each of these. Now we go across and down, so 2, 0, so it's going to be 2, 5, and 5, and then we go 0, minus 2, 0, minus 2, 0, and 0. Okay, so this is going to be 2, 2, sorry, 2 minus 2, so here. 5 minus 2 here, 5, 0 here. So there we can see a reflection in the line in the x-axis, the x-axis, or the line y equals 0. Now let's have a look at reflection in the line y equals x. So again, the points are 2, 2, 5, 2, and 5, 0, and a reflection in the line y equals x is 0, 1, 1, 0. So it looks like that. So now I go, that's 0, that's 2, and I go to this one, so 0 and 2, and finally 0 and 0, and you can see what's happening. So that's 2 and 0, 5 and 0, 5 and 0. So our coordinates are 2, 2, so here, 2, 5 here, and 0, 5 here. So you can see there, that's a reflection in the line y equals x. Now let's reflect in the line y equals negative x. And you should be able to see what's happening. 0 minus 2, 0 minus 2, 0, 0. We've got there minus 2 plus 0, minus 5 plus 0, and minus 5 plus 0. So there we have it. So minus 2, 2 is here, minus 2, minus 5 is there, and 0 minus 5 is there. Okay, and that is a reflection in the line y equals negative x there. Okay, so you can see now that's how those transformations are applied just to shapes with those coordinates. And you can always apply them to those shapes, but in general we look at the vectors 0, 1, 0, 1 and 1, 0. We look at those two vectors, but that is how I would apply them to any old shape. Now let's have a look at some rotations. Now a rotation matrix looks like this. So cos theta, sine theta, minus sine theta, cos theta. Okay, so this has like an invariant point of 0, 0. That's the only invariant point. When theta doesn't equal 180, so it's a different rotation, there are no invariant lines. When theta equals 180, then any line passing through the origin is an invariant line, and that's it. Okay, this formula, this general formula, is given in the formula booklet. Okay, so you don't have to learn it, but just keep using it and learn it, because it does make a lot of sense and a lot of use to know it. So let's look at kind of applying this. So if I wanted to do a 180 degree turn, so that would be cos of 180 minus sine of 180, sine of 180, and cos of 180. So cos of 180 is -1, sine of 180 is 0, so those two are 0, and cos of 180 is -1. So it's like reflecting in the y-axis and then reflecting in the x-axis, or vice versa. Okay, and that would give me the 180 degrees. So if I think about it and apply it to this one, so -1, 0, 0, -1, and applying it to 2, 2, 5, 2, and 5, 0, it will become -2, -5, -5, and it will become -2, -2, and 0. So -2, 2 is here, -5, 2 is here, and -5, 0 is here. And that is a rotation of 180 degrees, so either clockwise or clockwise or anti-clockwise, and I would have this shape. Okay, so that's a rotation of 180 degrees. Now obviously if I had a rotation of say 30 degrees, so that would be cos 30 sine 30 minus sine 30 cos 30. Okay, so cos of 30 is √3/2, and sine of 30 is 1/2. Okay, so this will give me a 30-degree rotation. Now, I haven't actually talked about which direction rotation it goes, but let's have a look with this one. So apply this to 2, 2, 5, 2, and 5, 0. And we get √3 times 2 minus 1, which is √3 minus 1. I'll just do this quickly. So that's what my values end up and what they roughly are as decimals to 2 decimal places. Now I'll plot them on the graph. Now it looks something like this. My diagram's a little bit off, but it's maybe not the best diagram really, but it's a rotation of 30 degrees anti-clockwise. about the origin. Let's have a look at an easier one. Let's look at 90 degrees. Okay, so cos 90 sine 90 minus sine 90 cos of 90. So cos of 90 is 0, sine of 90 is 1. So we get this. So applying it to our coordinates here, we get, so 0 minus 2, 0. We get 2, we get 5, we get 5. So it goes to minus 2, 2, minus 2, 5, and 0, 5, like that. And you can see that if I rotate this about the origin anti-clockwise, I'd end up with this shape here. So that is the rotations. Now, when I'm given a matrix such as this, and I want to work out what the angle of rotation is, I need to compare it to the original. So the original is my cos theta sine theta minus sine theta cos theta. Okay, now when I'm comparing, if I just compare the one angle here, cos theta equals root 2 over 2, I'll get theta equals 45 degrees. But if I compare the sine theta, so this bottom left, it's minus root 2 over 2. That gives me theta is minus 45 degrees when I go to my calculator. Okay, now we know that, for sine theta to equal this negative root 2 over 2, it happens in two places. So if I think of my cast diagram, and this is my 45 degrees, sine is going to be negative here and here. So sine is going to be negative at 225 and 315. Now I'm going to write this in black. Cos is going to be positive because this cos is positive here, 45, and here 315. So what I'm looking for is what one agrees with both. This one. So they're both correct here. So sine theta being negative and cos theta being positive is correct in this quadrant. So my angle theta is theta that's in this quadrant. So in this case, 360 minus 45, so at 315. Okay, so you've got to, compare these with the values and just think of your cast rule. Okay, so cos and sine, look at them. If they're both positive, it's going to be here. In this case, cos positive, sine negative, it's going to be here. They're both negative, it'll be here. Sine is positive, cos is negative, it's going to be here. Okay, so you can use that then to find out the angle. So the angle is 315. So it's a rotation about the origin anti-clockwise, and it's 315 degrees. So 315 degree rotation about the origin anti-clockwise. And that is what that matrix stands for. Now, I feel like I've talked a lot, although that's kind of what you do on YouTube, but I think it's time to give you a few questions to try yourselves. Obviously, if you've, I don't know about enjoyed the video, but found it useful, smash that like button. If you're yet to subscribe now. And if you want to help me out financially, hit that join button. Otherwise, let's look at the questions. Okay, there are 4 questions for you. Pause the video now to do these 3. Then the 4th one will appear next, and the answers are at the end as usual. Okay, so part A. So A represents a reflection in the x-axis, and B is not a reflection, it's a rotation. 270 degrees anti-clockwise about the origin. Okay, B. The point 32 is transformed by A. So 1, 0, 0, minus 1, and the point is 3, 2. So that goes to 3 minus 2. And C, the point AB is transformed by matrix B. So matrix B is that, the point AB. Okay, so first let's do this. So it's going to be 0, A, so it's going to be B, and then minus A to that, and that is equal to A minus 3B, 2A minus 2B. So A minus 3B equals B, and 2A minus 2B equals minus A. So 3A equals 2B, and on this one A equals 4B. So substituting it in, it's going to be 12B equals 2B, or 6B equals B. B's are going to cancel. It's going to be 0, isn't it? So B equals 0. It's the only way to make them equal. And if B equals 0, A then equals 0. So it's 0 and 0. It's a bit of a weird one, but that was actually in a previous exam paper. Just goes to show they put some weird things in there. Right, on to question 2. So we know cos theta, sine theta minus sine theta cos theta. So I always go with these two. So cos theta equals minus 1 over root 2, and sine theta equals minus 1 over root 2. So looking at the cast, where cos and sine are both negative, is here. So between 180 and 270 is what my angle is going to be. And if I put the positive version of this into the calculator, I get that the angle is 45 degrees. So 180 plus theta, so 180 plus 45 is 225. So it's 225 anti-clockwise about the origin. So rotate it. Okay. Right, part B. M transforms the point PQ onto that point. Find P and Q. So we've got minus, if I just write this out. So this times P and Q, and it's going to equal minus root 2 and minus 2 root 2. So working out the left side, we've got minus P over root 2 plus Q over root 2 minus P over root 2 minus Q over root 2. So Q over root 2 minus P over root 2 equals minus root 2. So let's take out the root 2's here. And then multiply by root 2, we get Q minus P equals minus 2. Now let's do the same with the bottom ones. So let's take the root 1 over root 2 out, so we get minus P minus Q equals minus 2 root 2. Times by root 2 will give me minus P minus Q equals minus 4, or P plus Q equals 4. Now add these two together, the Q's will give me 2Q. So it's equation 1 and equation 2, and we're adding them. So we get 2Q, the P's will cancel, and 4 and minus 2 is 2. So Q equals 1, therefore P equals 3. And there we have it for P and Q. So for part A, you've got to remember cos theta, sine theta, minus sine theta, cos theta. Now 90 degrees clockwise is 270 degrees anti-clockwise. Okay, so we want cos of 270 minus sine of 270 sine 270 cos 270. Now cos of 270 is 0, so these two are 0. Sine of 270 is negative 1, so that's negative 1, and this is minus minus 1, so it's 1. So that is that, and then 210 degrees anti-clockwise. Well, you can actually, without thinking about it, you can just put that in. So cos 210 sine 210 minus sine 210 cos 210. So you can plug it in. So cos 210 is root 3 over, or negative root 3 over 2. And sine 210 is negative a half. So that become positive up there. So that's one way of doing it. Equally, you can think of your cast diagram. 210 is here, that's 180, so that's 30 degrees. So the angle's 30 degrees and they're both negative. So you could then just write them out from there. So that is question 3 done. Okay, so part A, transform by matrix A, that is a reflection. In the line y equals x. Now, 3 invariant lines. Well, all the points, invariant points, are on the line y equals x, so y equals x will also be an invariant line. And then it's just y equals minus x, isn't it? So y equals minus x plus k. So y equals minus x, y equals minus x plus 1, or any of those, you know, from there on out. Okay, for A50, let's first look at A2. So that's 0, 1, 1, 0 times by 0, 1, 1, 0. So 0 times 0, 1 times 1, that's going to be 1. 0 times 1, 1 times, so that's 0. That's 0, 1. So that's going to be what A2 is. If we look at A3, it'll be what we just had times by 0, 1, 1, 0, won't it? Okay, which is the identity times A3. So it's going to be that again. So, you know, like this is just the identity matrix. This one now is the original starting one. So every odd one is going to be this. Every even one is going to be this. So A50 is going to be I, which is 1, 0, 0, 1. Okay, and that is how we do question 4. Again, this was a past paper question, or part of it. Now, that's the end of this video. It's going to go out maybe half an hour later than I have been doing them. I do apologise for that. I will try and get back on track for the next one.